So let's talk about system states now. A system state then is just the properties of the system at one particular value. So here's our piston cylinder device. I've laid it on its side this time. This could be the piston cylinder in your car's engine. Of course, the cylinder is pretty long for that, but bear with me. So we've got a gas above the piston, and that gas is what we're calling our system. Maybe it has some oxygen, some nitrogen, some gasoline that's been vaporized, hopefully at this point. But that system, when we measure, let's say we measure the pressure in that system. Well, that is associated with one state, right? If I were to take that piston and compress the gas, which your engine actually does, then the pressure is going to go up, and that would be a different state. Now, of course, I need more than just pressure to define a state. I need pressure and, say, volume and temperature. These collections of properties at one value is called a system state. Okay. Now, a simple compressible system is a system where we're going to neglect some stuff. That's why it's simple. I can give you this as an example using your car again. I'm sorry I go to your car so much, but it has so many different aspects that apply to thermo. It's very convenient. Imagine in your car you're going around a corner, okay? So let's say you're a speed demon. You're going around the corner just as quickly as you can, okay? So you're hugging the curve, tires squealing, going around a corner. If you think about the gasoline in the gas tank, well, it's a liquid. It's going to slosh around some. And if you're interested in the motion of that liquid, then the motion of the car around the corner is probably important. But now let's consider the fluid above the piston in the engine. Now, if you're going fairly fast, your engine's moving fairly fast, and if you've ever stopped to think about how fast a piston moves up and down in the cylinder that it rides in, it's pretty doggone fast. It's actually pretty impressive what kind of accelerations that piston has to experience and not fall apart. Anyway, now let's consider the gas above the piston. You're still going around your curve real fast, right? And there's air molecules in the gas. And let's think about, you're going around the curve, those air molecules, are they really going to kind of slosh to one side like the gasoline does? Or is that motion, that acceleration, is that really significant by comparison to the acceleration being caused by the piston? Probably not. Right? The acceleration of the gases being caused by the piston's motion is going to be a heck of a lot higher than their acceleration due to the bulk motion of the vehicle. And so that's why we say that we typically neglect motion. Now, we're not neglecting all motion. The motion on the molecular level is still interesting. As a matter of fact, it turns out that actually when those gases are hot, on the molecular level, they're moving so quickly that the motion of the piston itself is not all that interesting. Okay, so when we say we're neglecting motion, we're actually neglecting quite a lot here, including the motion of the piston. And I hope I didn't confuse you there. I used the motion of the piston to convince you that the motion of the vehicle is not really all that important or worth considering. And then I switched around and said, oh, by the way, the motion of the piston is not all that it's not all that important to consider. Well, how can that be? Well, if you've ever watched a slow motion video of a gun firing a bullet and you see the bullet leave the chamber, you'll understand this, but you need to watch it again in a little more detail. So I've got that video in the optional videos to watch. I think it's a Mythbusters video, and it's pretty good. It's only about a minute long or so. So you know what, I think I'm going to make that one not just recommended but required. So I'm going to add that into the list. But anyway, if you watch very carefully, what you'll notice is you'll see the bullet. It starts to come out of the gun. You'll see the tip come out. And as soon as the rear of the bullet has cleared the barrel, what you'll notice is that there is this very quick puff of gases. Some of it burned, some of it unburned, all of it hot, right? And that's what's pushing the piston, or pushing, well, it is a piston. The bullet is a piston coming out of the chain, or not the chamber, but the barrel, because the barrel just acts like a cylinder. That's all it really is. So think about it. Well, the gases there are certainly moving faster than the bullet. They're what pushed the bullet out so fast in the first place, right? In the same way, the gases on the molecular level in the piston cylinder device are moving a lot faster than the piston, and so motion is something that we can neglect. In a similar way, is the pressure difference between the top and bottom of the cylinder all that important due to gravitation, right? I mean, if you think about the pressure difference of the air in our atmosphere, Yeah, sure. On ground level, there's a much higher pressure than, say, if you go up, 30, 40, 50,000 feet in the air. And that's, of course, due to gravitation, right? Thank God for gravity, otherwise we wouldn't have any air on this planet. So, and I don't know about you, but I like breathing. So, but gravitation is another one of those things that over a short height difference doesn't really cause much of a pressure difference in the cylinder, so we'll neglect gravitation's effects. Magnetic field, surface tension, electric fields, all these things do have a small effect on the fluids that we're going to study, but usually they are so small that we simply neglect them all. So when we say simple compressible system, these are the sorts of things that we're neglecting. They're all small effects that we can safely neglect and ignore. So finally, we can state or we can define the state postulate. It is this: the state of a simple compressible system is completely specified by two independent intensive properties. Now, remember before I said specific properties? Well, specific properties are properties that are also intensive. They do not depend on the extent of the system. So another name for specific properties is intensive properties. Okay, so if we have two independent properties, say pressure and temperature, well then we can know everything else we want to know about the fluid, as long as it's a simple compressible fluid. Okay, now wait a second. Let's think about this for a minute. Is this something you already knew? Actually, it kind of is. By the time you get to this course, you've seen the ideal gas law. How does the ideal gas law go? Well, we'll get to it later in the course, but for right now, it's PV equals nRT. That's the way you learned it, right? If you're in a chemistry class. In this class, we're going to use PV equals mRT. Don't worry about that. I'll explain those details a little bit later. It's just a more convenient formulation, okay? But think about it. If I just have a simple piston cylinder device with air above the piston, so it's a simple compressible system, well, if I know the pressure and temperature of the air, wait a second, PV equals mRT, if I know how much mass is in the system, I can say how much volume there is, right, from the ideal gas law. Now you can say, well, isn't mass another property of the system? In a sense it is, but I'll show this to you later again, but if you take that mass and divide the volume by the mass, guess what you've got? You've got specific volume. So we'll actually use the ideal gas law in the form P multiplied by lowercase v, which is the ratio of the volume to mass, equals RT. We'll use it where all of the variables, the pressure, the volume, and the temperature, are intensive properties. Okay? And so it'll turn out that if you have two independent intensive properties, like pressure and specific volume, or temperature and pressure, you can calculate the other one. It turns out there are other properties as well. There are things like internal energy. So the energy per unit mass is a specific property as well. It turns out if I know the pressure and temperature of air, I can tell you how much specific energy is in that air, which is really interesting. I can tell you other properties, things we haven't talked about yet, like entropy. Okay, we haven't even touched that yet or defined it. We will a little bit later. But all of these things are related to each other, and it's really nice to know that I don't have to remember, 5 or 6 different values of properties in a system. Those properties depend upon one another. Now I know that this probably doesn't mean a whole lot to you yet, and a lot of this course is like that, unfortunately, and that's the other part that makes thermo seem very confusing and difficult to study. But I'm trying to tie things together as much as I can. You may want to come back periodically and watch some of these videos again, or try to write down some notes, and if you get to a point where you go, I think he said something about this, try to go back and find that, or go to the text, look up that particular term or terms in the index and read what your author has to say about it, because he'll say a lot of similar things, of course, to what I'm saying. Maybe that'll jog your memory and things will start to fit together. That's one of the things that makes this course difficult. There's so many pieces that have to fit together at one time. For a lot of students, it seems like a lot of pieces of the puzzle that never get put together to make a cohesive picture. I guess that's kind of why we have 2 separate thermo classes then. But anyway. Alright, so now we can define equilibrium states. What do we mean? Well, we've learned that we have systems, and those systems have properties that are interesting to us. What is an equilibrium state? Well, what is a state, first of all? A state is a collection of properties at one particular value for each of those properties. So what is an equilibrium state? Well, an equilibrium state is something that we're going to assume always occurs, okay, at least in this class. Now, it's an idealization. We're making things easier on ourselves, and in just a minute I'll show you that obviously this doesn't happen in the real world, but it will get us closer to understanding how engines really work and how the world really works as we go along. So, what is an equilibrium state? Well, we're going to assume that when we're looking at a system, and that system is at one state, then the temperature everywhere within that system is the same. Okay, so that's thermal equilibrium. In other words, there's no higher temperature in one corner of the cylinder than in another. Energy has equilibrated out. It's the same everywhere. There's no pressure difference, as the pressure is not higher on one end of the cylinder than the other, and so forth. There's phase equilibrium. We don't have some vapor that's about to change to liquid and it's going to change in the next few seconds. There's chemical equilibrium where things aren't reacting anymore, and so these equilibrium states require equilibrium of all these different properties, these things, right? The temperature, the force and pressure, the chemical species. Now, what about in a real engine? What really happens above the piston cylinder device? Well, look up at the schematic I've got. It's a cross section with a spark plug in it at the top, and you see the piston is at top dead center. It's as high in the cylinder as it's going to go, so the system is really compressed here. And imagine what happens once the vapor fuel mixture and air is ignited by the spark plug. Well, I don't know if you know this, but in a real engine, you actually don't want all of the fuel to burn at exactly the same time. If that happens, you actually have something in your engine called detonation. And detonation is kind of like taking a hammer and just beating the top of the piston every time the piston comes back up. Engines don't last very long with detonation. And so it turns out that actually some high-performance cars, what can happen is you can end up with so much air and fuel that when you compress it, if you compress it too much, it gets so hot that the air and fuel just burns all at once without the spark plug starting the burn. And that is detonation. And so what they typically do is they have a couple of sensors to detect detonation, then they'll retard the timing if necessary. Don't worry about what all that means. It's just a way to try and prevent detonation. But also what they'll do is they'll require high-octane fuel. And you might think, well, I wish I could afford high-octane fuel. It's got to be better, right? It's got to be better for my engine and a better thing. Well, maybe, maybe not. Actually, high-octane fuel is fuel that is harder to burn than regular fuel. It's actually a molecule that's more closed on itself, so the oxygen has to attack from multiple sides more than once, so that the fuel burning rate slows down, and that helps prevent detonation. So you just need to use the fuel that the manufacturer calls for in your car, and if that's high-octane fuel, fine. But what really happens when the burning of the fuel begins is the spark plug lights up the fuel in one area, right? It's just a small spark in one area of the cylinder. And so the air-fuel mixture starts to burn from that point outward, okay? And so you can kind of see the pressure wave and the flame front advancing. And what happens is the pressure behind that pressure wave near the spark plug all of a sudden spikes, right? It goes up really fast because the temperature of the gases in that region are rapidly going up. And so there's actually a pressure wave, kind of like, not a shock wave exactly, but kind of like what you've probably seen in explosion videos where, you know, you've seen factories explode and things, and you can see the pressure wave move across the landscape. That's kind of what's going on here, okay, but hopefully not quite as violent. Anyway, so that pressure wave expands out, and so if you think about the pressure in front of that pressure wave is much lower than the pressure behind it. So is that pressure or mechanical equilibrium? No, it's not. So in the real world, we don't always, in fact, we rarely have these equilibrium states that we would like. But we have to start somewhere. And so that's what we're doing with this. So these things don't really, these equilibrium states technically don't exist in the real world. There can be other reasons for pressure imbalance. There can, obviously there's chemical imbalance, right? The fuel behind the flame front has pretty much burned, but the fuel in front of it has not. The air and fuel mixture is still there and has yet to burn until the flame moves forward and starts the reaction in other areas of the cylinder. So now we can define a uniform system. A uniform system is something where no property is different within any point inside of the system. And that's closely related to a equilibrium state. Okay? So the example I use here to help students understand is pancakes. Now I don't know about you guys, but I love pancakes. And I found a book at the library many years ago. There was a copycat recipe book, and so they had different ways of making, food you'd find at restaurants in your home, and it was supposed to taste very much like what you could buy in the restaurant. Now some of it did, some of it didn't, but the recipe that they had for International House of Pancakes was actually really good. It was spot on, tasted exactly like it. Well, it did after I figured a few things out. You see, I started out trying to cook the pancakes in just a skillet on the stove, and I never could get good results. The center of the pancake would be pretty much burned, and the outside would be hardly cooked. I couldn't get that nice, even golden brown across the surface of the pancake. Well, it just so happened that some friends of mine gave me a griddle for cooking things. And one day I thought, I wonder if the reason that I can't cook pancakes well is because the center of the pan is really hot and the outside, the rest of the surface of the pan is actually fairly cool by comparison. So I grabbed my infrared thermometer, and you'll learn more about how those work a little bit later, but I grabbed it, put the pan on the stove, and measured the temperature. The center temperature was about, I think, 400 or 500 degrees, and the outer temperature was 200-300 degrees. And I thought, well, no wonder I can't cook pancakes worth a darn. This pan has a very different temperature across its surface. When I took out the griddle instead and heated it up, the heating element actually runs underneath the entire base. You can see a pancake griddle here. It actually runs underneath the entire surface, and when I turned it on and used my thermometer, I found that the temperature did not vary hardly at all. It was a very nice uniform system. And so if you want to understand uniform systems, think about it this way. It doesn't matter where I moved in the X or the Y direction along the surface of the griddle, I got the same measure of the property being temperature. And once I put my pancake batter on that, perfect golden brown pancakes. Tasted delicious. So if you're interested, I have posted my pancake recipe because students have asked for it in the past. I've got a link to the copycat recipe as well. It's still online last I checked. But if you want to know how to make great IHOP tasting pancakes, well, every time you make them, now you're going to think about uniform systems, and you know what a uniform system is. Okay, quasi-equilibrium processes. What is this? Well, if we have a system that's in one state, that's not really all that interesting. We want the system to change states. In other words, you think about the gases we were talking about in your car above the piston in the cylinder. Well, those gases need to be burned, right? We need to compress them at first. We want the pressure to go up. So if you look from left to right, the piston has moved from left to right. The volume of the system has decreased. You can see that on the volume axis, and the piston lines up with the two states. And of course the pressure in the system is going to increase. So we've gone from state 1 to state 2. Both state 1 and state 2 are equilibrium states. At least that's what we're assuming in this class. And we're going to assume most of the time that the path that the system moves through consists of a whole lot of equilibrium states. So this is a quasi-equilibrium process. We're assuming that the system reaches or attains equilibrium as we move through the process path. Why is that important? Well, I don't have a good way to explain to you why that is important now. You'll see later when we talk about irreversibilities. But for now, what you really need to know is that it really means that we're assuming that the motion, the mechanical, the time constant is very, very long. So the system, the gases, move faster than the bulk machine that we're dealing with. Okay, if that makes any sense, that's really what we're trying to get at here. So it's called a quasi-equilibrium process since the system moves through equilibrium states. Now there are simpler types of processes that we will want to consider. And these simpler processes often revolve around one particular property of the system remaining constant. So you might guess, this is kind of a matching game here, you might guess what isothermal means. Isothermal means constant temperature. That's right, that's what it means, okay? Isobaric, what do you think that is? Well, if you know anything about pressure, you know that bar is a measure of pressure, and so isobaric means constant pressure. Isochoric or isometric means constant volume, and isentropic means constant entropy. Now you don't know what entropy is yet, that's okay. But these are just special types of processes where one particular property of the system remains constant. And so we call a process that the system remains at one temperature, we call that an isothermal process. If the system remains at a constant volume and yet changes states, and so other properties change, we call that an isochoric or isometric process. Okay, if the system changes states but the pressure remains constant, then that is an isobaric process or a constant pressure process. There are other types of processes, one being a steady flow process. Now, the interesting thing here is that this is not a uniform system. If you've ever seen a system like this is kind of from my background. My undergraduate degree is chemical engineering, so we talked a lot about continuous stirred tank reactors. And that's what you're looking at here, is a reactor where it's typically a jacketed reactor, so you can cool it or heat it, whatever is needed for the reaction to take place. But feed is introduced continuously into this tank. A stirrer stirs things up so the reaction can take place, and then product is constantly withdrawn. And whatever the reaction is, maybe it's A goes to B, whatever, it doesn't matter. But the point is, if I were to look and sample at any point in this system, I'd get something different than some other point. The feed is obviously different than the product, otherwise what's the point of this tank, right? So it doesn't have the property of being uniform. It's not a uniform system, but if this is a continuous process, then there's no change with respect to time of any property within the system. So if I were to look at the feed's properties, its temperature, its pressure, its composition now versus an hour later, I would find no change in that composition. Okay, if I were to look at the pressure right at the tip of the stirring rod now and 5 hours later, it would be exactly the same, because the idea of a steady flow process is that there's no change of any property with respect to time. So we started off with systems and how they can have states, right, where it's a collection of properties. We realized that we can move from one state to another, and that is a process, but we can actually tie multiple processes together so that the system returns to its original state. And so you might see here, you might recognize these two things. The left-hand picture is actually a Wankel engine. Now the sort of triangular, can't remember the name of it, the triangular shape that rotate, the rotor that rotates around is not actually shown here. What's shown instead is the system itself. And so we've got initially an intake of fresh air and fuel. We've got compression. I'm trying to time it. Then the spark plugs light it up. Now we've got expansion, and then exhaust out the exhaust port, and then the rotor comes back around. Of course, what's interesting about a Wankel engine like that is that the rotor has three sides. And so those three sides actually are kind of like a piston on every side, where a different portion of the cycle is occurring. Well, we can actually analyze this, or even the typical piston cylinder cycle, with a PV diagram. In fact, this is what's called the Otto cycle. Now, don't worry about it right now. We'll get to it later. But the Otto cycle consists of four particular processes. Two of those processes are isochoric or constant volume processes. Notice from state 2 to state 3, that process occurs at constant volume, because look, that line all lines up with one volume on the volume axis. Okay. Now there are also a couple of other processes. The compression process is the process from state 1 to state 2, and that process is an isentropic process. And you'll understand more later what that really means and why that's important for analyzing engines. Okay, so the kind of the cap on this, the crown of it all, of the class, is the cycle analysis that we get to in Chapter 7. But you have to understand all the foundation and all the thermodynamic stuff leading up to it. So I promise we'll get to it. It's just we have a lot to learn before we get there.